Hi, it's Kevin from Kevin's Classroom. We're going to look at the Maxwell-Boltzmann curve over here, which basically proves that an increase in temperature of a mixture, of a reaction, is going to increase the rate of the reaction. So how do we do this? We say, right, this is the percentage over here of molecules in the substance. Okay? That's the percentage of molecules. On this side over here is my kinetic energy. And kinetic energy, just let me write that, EK, is a proxy for temperature. Right? Why? Because the faster we go, the more temperature we add, the more excited they get and the faster they go. And I'm then going to draw this, and it never turns out exactly great, but just bear with me. Let us say that this is the situation at T1. What we're saying that this is the average temperature of our current situation. Then what I'm going to do, this is T1 over here, let's say, or the kinetic energy. The next thing I'm going to do is I'm going to move this over like so, and let me get this better like that. Okay. Now what I can do, I should actually bring that down a little more. I always flatten it off too much. So now I say, right, initially I had an activation energy over here. So this is the activation energy, this is the temperature at which we are going to get the actual components split up. And you can see that at that point, if I use black you can see that that's the area to the right. Now, please remember in this thing here, when we look at it, let me just erase that. Let's always just look at it and say, remember, this is like a distribution. This is a distribution curve. Okay? So it's a distribution curve. What do I mean? I mean the area under the curve is the total number of particles. It's like a histogram or a frequency distribution curve in stats. If you look at the area underneath, it must have everybody in it. Now I go and I delta T this thing. Okay, I'm now going to go up to T2. All right, and at T2, let me just get it to this one. Okay, I have changed it. Let us say I've gone to here now. Okay, at T2, actually, I'd rather put it at the top of the curve. Okay, I've changed it to T2 over here. Okay, this is my T2. This is the new average temperature of the mix. So I've gone to T2. There you can see there's delta T there. Gone from the one to the other. What has happened up here? We have got extra area under the curve. So if I now compare, let's just leave it there. If we compare the black with the orange or the red, you can see that at the previous temperature T1, we had a small area under curve. Okay? At T2, we had a larger area, which means more molecules are above the activation energy required. The last thing to note about this character here is please notice this slump, that drop, or vice versa if you're going the opposite way. The drop must be so that when it's in the mold, if you think of it as a jelly mountain in the mold, when you take it out, it flops, but the total volume of jelly remains the same. So the total area under the curve must be the same once you have removed it from the mold. And that is how we deal. That is the principle of the Maxwell-Boltzmann curve. Cheers. Enjoy. Bye.